Today we will start with mechanical waves. Let's clarify something in regards to mechanical waves. Mechanical waves carry, when they move from one point to the other, they carry energy. So as they are moving from point A to point B, they carry energy with them, okay? And in order for a mechanical wave to move from point A to point B, it needs a medium. So meaning that it needs some sort of material in between those 2 points. If we have vacuum, then mechanical waves are not able to transmit that energy from point A to point B. So in a difference with electromagnetic waves, which you will see on physics 30, mechanical waves needs a medium to be transferring that or carrying that energy from point A to point B. So mechanical waves needs medium. When we say medium, means any material. Air is a material. Water is a material. Anything that has particles on it, it's called a medium. In a vacuum, mechanical waves cannot be transmitting the energy from point A to point B. An example on this is the sound waves. If you are in a vacuum, you can scream as much as you can, and no one that is in a vacuum can hear you. In the same medium, vacuum can hear you. Because there is no medium to transmit the energy from you to someone else being on the same room in vacuum. But you can hear if you are in air. So as soon as you see some atmosphere, some air presence, then you will be able to hear what the other is saying. Mechanical wave in a ripple. So let's say that you have a pond and then it's quiet, and then you just cause a motion of the particles and then you see the ripple. If this is a vacuum, then you will not see those ripples in the water. Okay. There are 2 types of mechanical waves. One that is known as the transverse wave, and the other one that is known as the longitudinal waves. So transverse waves are the one that particles are moving in the same direction as the direction of the wave. So when you see it here, for transversal waves, the particles are moving perpendicular to the direction of the motion. So if the wave is moving on this direction, this is known as the wave direction. It is the direction in which the wave is transmitting the energy. The particles will move perpendicular to this direction. So this is the direction of wave, which is known in other words as the propagation of the wave. And this one is the direction of particles. The way that the particles are moving. So what do you see is you cause a motion here. Those are the particles, and then the particle obtain like a way that it moves like this. So it goes up and down, and then the wave moves in this case, east direction, but the particle moves up and down. Very common when you see ripple in the water. So the water is quiet, is no motion, and then a rock is thrown in that pond, or a motion is caused, and then what do you see is the ripple, which moves perpendicular to the direction of the particle. So you are moving it, the cause of the motion is going up and down, and the ripple is moving toward you, perpendicular to that motion. Now, the maximum motion of the particle is known as the amplitude. We kind of saw this when we had the simple harmonic motion. The second type of wave is that is known as the longitudinal wave. For the longitudinal wave, the particle and the wave motion are in the same direction. So, very common when you have a spring. If you have a spring, let's say in the horizontal surface, and it is no motion on the spring, and then what you do is you either compress it or expand the spring and let it go. What do you see? The particle is moving on the same direction as the wave. So it is, the wave is going through compression and expansion, compression, expansion, and which is the motion of the wave. So this is how the energy is transmitted, and the particles are moving on the same direction. What caused that wave to move is in the same direction as the wave motion. When we see the wave motion is the same as saying direction of motion, of wave, or direction of the propagation. Propagation of the wave. So this is the view that we have when we create a longitudinal wave, and then from the top, what we see is compressing, expansion, compressing, expansion. The distance between the two compressions, it's known as the amplitude as well of the wave. Okay, so now in terms of the wave pulses and what is a wave, the wave pulse is pretty much the amplitude that we are seeing in the wave. Okay, and the wave is what is created, in which way is it moving. So the amplitude of the wave can be positive if it is above the horizontal, or that is known as the no disturbance, or can be negative if it is below the horizontal. So we can say it's a negative wave pulse or a positive wave pulse based on the position that the wave is having. So if we have this as a non-disturbance, this line as the non-disturbance wave, then a wave that is moving like this, up and down, this may be a transversal wave. This will be a positive wave pulse, and this will be a negative wave pulse. But it doesn't matter what it is, the maximum length that, or the maximum depth or crest that the wave is reaching is known as the amplitude of the wave. And in order to avoid is the amplitude positive or is the amplitude negative, we just take the absolute value of this length the wave pulse, and then we say that this is the amplitude. When we are dealing with the absolute of the length of the wave pulse, then we are taking into the consideration only the length of the wave pulse being always positive. So the wave pulse with a positive and negative displacement, and the way that the wave is propagating is this one here, this direction here. And then we see a wave that is going from positive to negative pulse, creating. So when the particle is moving from negative to positive, and then negative, and then so on, is creating a wave, and the wave is propagating in the way that the energy is transmitted. Let's take a look at the wavelength, period, and frequency. Those are period and frequency are concepts that we discussed even at the simple harmonic motion, but not the wavelength. So if you have a wave that is the most understandable way to, the most common way to understand the waves is when we see a transversal wave, but this is applicable to both transversal and longitudinal waves. So if we have a wave, and it doesn't matter if it is transversal or longitudinal wave, then you will see that in an ideal situation, what will happen is that the wave will reach a positive wave pulse and then go through that equilibrium or non-disturbance position, and then head to the negative wave pulse, so positive, negative, and then move positive and negative, positive and negative. So as you see here, you have two consecutive positive waves, wave pulse, two consecutive wave pulse, which the distance between those two consecutive wave pulse is known as the wavelength. And the letter that we use for the wavelength is lambda. So this is how we write it, as lambda. So every 2 points, even the two consecutive negative wave pulses, will give us the wavelength in an ideal situation. No loss of energy is happening here. Or the distance between two consecutive going at the same way. So if this is increasing, then it is increasing again. Two consecutive points that has the same attitude, so either increasing or decreasing, because even if we go to those 2 points here, this point here and this point here, so the distance between the two will be known as the wavelength of the wave. And the units for the wavelength are in meter or nanometer or so on, but meters is the international system unit. On the other hand, what period is and frequency is the same logic as we did at simple harmonic motion. Period is the time that completes one, we said one revolution, now is one cycle. So the time that it goes from this point, point A, to point B is known as the period, or the time that it goes from point C to point D, or the time that it goes from point E to point F, or the time that it goes from point G to point H is known as the period of the wave. and frequency is the inverse. So we saw that period and frequency are inverse of each other. Okay. So when we have a wave like this, let's say, then you can say that the distance from point A to point B, and then you know that the wavelength is 29 millimeters. So you can say that the distance from point A to point B is 29 millimeters, or from point C to point D, CD is 29 millimeters, or from point E to point F is 29 millimeters. So it doesn't matter where is it. You can take any other points, and then you can take a point G and point H. So GH is as well 29 millimeters. Okay, so now this equation is known, that is found in your formula sheet. It is known as the universal wave equation. So it is true for any, universal means that is true for any wave. What is it saying? It's saying that the speed in which the wave is moving is equal to the product of the frequency and the wavelength. And this does make sense, because if we see that if we are assuming that the wave is moving in a uniform circular motion, then V will be delta V over delta T. But what is delta D, as we said, is the wavelength, and what is delta T is what is the period of the revolution. Now, since 1 over T is equal to the frequency, we can say that this is lambda times F, or you can say lambda over period. But the universal equation of the wave is known as the speed is equal to frequency times the wavelength. Now, the speed of a mechanical wave can be anything. Okay, in a difference with the speed of the electromagnetic waves, which you will see on physics 30 that are constant, the speed of a mechanical wave can be anything. Now let's see some example. A series of waves with wavelength of 2.5 meter have a frequency of 50. What is the speed? So the speed, frequency times wavelength. The frequency is 50 hertz. And the wavelength is 2.5 meters. What does that mean? 2.5 meters is that the time to complete one full circle for the wave is 2.5 meters, or not the time, the length that is completing one full circle is 2.5 meters. And what 50 hertz means is that we see this circle, this revolution completed in 1 second 50 times. And now in your calculator, 50 times 2.5 will be 125 meters per second. And even if you do the units here, so hertz are 1 over seconds. Wavelength is in meters. This is the frequency, and wavelength is in meters. And when you go meters times 1 over seconds will be equals to meters per second, which are the units for the speed. Is it clear? So now let's figure out what is the frequency. On this example, a wave with a wavelength of 10 meters has a speed of 300 meters per second. What is the frequency? So based on the universal equation of the wave, we can say that speed is equal to frequency times wavelength. And from here, we can find that the frequency is speed over the wavelength. And this will be 300 meters per second over 10 meters. And this will be 31 over seconds as the unit, or 30 hertz. Okay, so what does those number means in terms of the wavelength? If you have a wave that goes like this, the distance from the two tops or maximums is 10 meters. And we see this circle completed from point A to point B. This circle completed 30 times in 1 second. This is what the frequency of the wavelength of the wave means. Clear? Okay. Another phenomena that we notice that is happening in the waves is that is known as the interference. When two waves are moving in the opposite direction, they meet at a certain point. And what they do is they interfere between each other. And as the result of interference, you may see that is known as the constructive interference, when the two waves are added together, and then you see that you observe a bigger amplitude or wave pulse, or deconstructive interference, where they kind of cancel each other totally, or they the wave pulse is smaller than each of the wave pulses that the two waves had. So let's take a look at this this picture. So as you see here, you have two waves moving in the opposite direction. This is the first wave and this is the second wave. And when they meet here at this point, this is the meeting point. When they meet there, what is happening, the waves are meeting together and they are added the two pulses together to create a higher pulse, wave pulse, or higher amplitude, pretty much. And then after they meet, they go into their own direction. Since when they meet, they create a higher wave pulse than what the original had, then this is known as the constructive interference. But when we have a deconstructive interference, so now we have wave 1 here and wave 2 moving in opposite direction, and this is the meeting point. When they meet at this point here, what is happening is that they cancel each other. So on some cases, like in this one here, when the wave pulses are with the same amplitude, then they cancel each other. But if they are with different, so let's suppose that if you have a wave that is like this, then what will happen here at the midpoint, you will have a wave that will be smaller in amplitude or in the wave pulse. And when the two waves meet each other and the amplitude or the wave pulse is smaller than the original amplitude or wave pulse of the two waves, then we say that what is happening is that deconstructive interference. Is this clear?